Hello everyone and welcome to the final demonstration of my project LumiGuard. Let me first start with a simple question. How many times have you left a light on outside overnight, wasting electricity for no reason? Or maybe you felt the need for a little extra security lighting around your home that just works. No apps, just smart detection. That's the exact problem I set out to solve with this project. LumiGuard is a self-contained Arduino-powered smart security light that only turns on when it's actually needed and when motion is detected in dark conditions. It's designed to save energy, increase safety, and operate independently without any complex setup. In this video, I'll walk you through the full design journey from idea to enclosure and show you exactly how I built, tested, and verified this system from the ground up. Whether you're into electronics, DIY home security, or just curious about smart systems, this video has something for you. So let's get into it. The goal of this project was to design a smart security light that activates only in dark conditions and when motion is detected. It also includes manual test capability via a push button and a voltage monitoring system. To achieve all of this, I used the Arduino Uno as the main controller along with the following key components. A PIR motion sensor for movement detection, an LDR sensor for ambient light sensing, a voltage sensor for battery monitoring, a push button for manual testing, and a 12-volt LED light powered via a relay. I used a 12-volt battery as the power supply for my security light system. I first began by planning out the basic logic and component interactions using a flowchart and a block diagram. The flowchart helped me visualize how the system would behave in real time, starting with sensor initialization, checking for motion, evaluating ambient light conditions, and finally deciding whether to activate or deactivate the relay based on those inputs. At the same time, I created a block diagram to understand the physical and electrical connections between the Arduino Uno, the battery, and all attached modules, including the motion sensor, LDR, voltage sensor, relay, and push button. These diagrams gave me a clear roadmap to follow when wiring the components and writing the control logic in the project. Before moving to the hardware, I simulated the logic in Tinkercad first to verify its behavior. The relay triggered only in low light conditions and when motion was detected. The push button worked as intended, manually turning the light on and off. I also measured current usage in different states, with low power mode active during ideal daylight hours to conserve battery. Now let's take a look at the power requirements of the LumiGuard system. The primary power source used is the 12-volt lead-acid battery rated at 7 Ah. Based on the total power consumption, this battery is capable of powering the system continuously for around 14 to 15 hours, making it ideal for overnight security use. To ensure safe and stable operation, voltage regulation is handled by the Arduino Uno's onboard voltage regulator, which steps the 12-volt input down to 5V for the microcontroller and all 5-volt components like the sensors and relay control. Meanwhile, the relay module handles the switching of the 12-volt LED light separately. As shown in the table, the combined power usage of all components, including the Arduino, motion sensor, LDR, voltage sensor, relay, and LED light, adds up to approximately 5.73 watts. This careful power calculation helped ensure the system runs efficiently without overloading the battery. Firstly, I started by identifying all required components and creating a basic breadboard circuit. This allowed me to test how the motion and light sensors would behave in different conditions and how the relay would control the LED light. I tested the system using a 12-volt lead-acid battery. All components run at 5V except the LED, which runs at 12V through the relay. The LDR sensor was connected with a 10K ohm pull-down resistor, and the voltage sensor was calibrated to convert analog readings into real battery voltage values. The PIR sensor was positioned to detect movement up to 7 meters. After confirming the design on the breadboard, I transferred all components to a proto board and soldered the connections for better durability. This eliminated loose wires and made the system stable for long-term use. Each sensor, the relay, and the Arduino were securely wired and tested again. I adjusted the LDR threshold to 500 based on real-world lighting and tuned the PIR sensor sensitivity using the onboard potentiometer. With the circuit finalized, I designed a custom 3D printed box to house the components using CAD software. The enclosure has a cutout for the PIR motion sensor, an opening for the LED, and push button. The dimensions of this box are 12 inches for the length, 8 inches for the breadth, and 5 inches for the height. Now for the demonstration. When it's dark and motion is detected, the system automatically turns on the LED security light. If there's no motion, the light stays off. You can also press the push button to manually turn the light on or off for testing. The voltage sensor continuously monitors the battery. As you can see here, I've transformed a 12-volt adapter into a battery charger to charge the 12-volt battery. Now let's take a quick look at the final version of the Arduino code used in the LumiGuard system. At the top, we define the pins connected to all the components. The LDR is connected to analog pin A0. The motion sensor is connected to digital pin D2. The relay to D7. The push button to D3. And the voltage sensor to analog pin A1. We also define a relay state variable to help us toggle the light manually. We also set a light threshold value, in this case 326, which was chosen based on live testing in different light conditions. Inside the setup function, we configure the sensor and relay pins as input or output accordingly and begin serial communication for monitoring data in the serial monitor. In the loop function, the Arduino continuously reads values from all the sensors. It checks the LDR for ambient light level, the PIR for motion, the voltage sensor for battery levels, and the push button for manual input. Based on these readings, the code performs three main tasks. If the light level is below the threshold and motion is detected, the relay is activated and the light turns on. If it's bright or no motion is detected, the light stays off. If the push button is pressed, the relay toggles the light manually. This is useful for testing or emergency use. The voltage reading is also calculated and printed to the serial monitor so we can monitor battery levels in real time. Let's have a look at the two serial monitor test outputs. When the LDR value drops below the threshold, which happens when the sensor is covered or in the dark, the system responds with light on and the relay activates the LED. When the sensor is uncovered or exposed to bright light, the LDR readings go higher and the output switches to light off. This confirms the light detection is working as expected and the relay toggles accordingly. For the battery voltage sensor readings, when the relay is on and the LED is drawing power, the voltage drops slightly, ranging from 10.68 to 10.75 volts. When the relay is off, the voltage reading increases, showing values between 10.8 and 10.85 volts. This confirms that the voltage sensor is correctly monitoring the battery's charge status in real time. To verify the functionality of LumiGuard in real time, I'll be demonstrating the system with the help of a friend. Finally, let's have a look at the brochure. As shown earlier, LumiGuard uses a PIR motion sensor, an LDR sensor for light level sensing, a voltage sensor for battery monitoring, and a push button for manual control. All the components are powered by a 12-volt lead-acid battery and neatly enclosed in a 3D printed box for durability and portability. The brochure outlines that the system turns the light on only when it's dark and motion is detected, allows manual override with the push button, monitors battery voltage in real time, uses a 5-volt relay to switch a 12-volt LED light. The electrical and mechanical specifications, including power consumption of 5.70 watts, operating voltage of 5 and 12 volt, and compact enclosure dimensions, have all been met and verified in the demo. The connection layout, component details, and real-time working of the system exactly match what's documented in the brochure. In conclusion, LumiGuard is more than just a student project. It's a practical, energy-efficient lighting solution designed for real-world use. Whether it's installed at your front porch, garage, backyard, or staircase, LumiGuard offers smart illumination only when it's needed, saving power while enhancing safety. Thank you for watching.